Exercise 8. Calculate the maximum internal crack length allowable for a 7075 T651 aluminium alloy component that is loaded to a stress 1/2 of its yield strength. Assume that the value of Y is 1.35, yield strength of this alloy is 495 megapascal, and fracture toughness is 24 megapascal square root of meter. So we know this. Okay. Fracture toughness Kc is equal to Y sigma C del pi A. So we know these values. Okay, 24 megapascal. Y is given as 1.35, and the stress is the limiting stress. Okay, critical stress 495 megapascal, and the maximum loading which is applied is 1/2. Okay, so it should be 495 divided by 2 pi A. So A, of course, we need to find maximum internal crack length. So in this case, we can find the value of A. Hello. Yes. But here actually there is one thing I need to consider, is that it has been asked that the internal crack length. Okay, so if it is the internal crack length, so here the value which I will find, that will be over here, will be for A. Okay, so it will be 0.0016. Okay, 164 millimeter. So this is this half of the internal crack length, because the internal crack length is not A, internal crack length is 2A. Okay, so whatever the answer which I will get from here, I need to double that. So it will be 0.0033 meter approximately. Or in other words, it will be 0. It will be 3.3 millimeter. Yeah, just use this. Okay, so 3.3 millimeter will be the length of the internal crack. Exercise 9. A fatigue test was conducted in which the mean stress was 50 megapascal and the stress amplitude was 225 megapascal. So compute the maximum and minimum stress levels, and then compute the stress ratio, compute the magnitude of stress range. So compute the maximum and minimum stress levels. So sigma max we need to find, sigma minimum we need to find. So this the mean stress. So we know that the mean stress is equal to sigma max plus sigma min over 2. This is the mean stress. So from this equation we know that sigma max plus sigma min is equal to 2 times the sigma. So mean, so it means it is equal to 100. So this is one equation. And the stress amplitude is basically sigma max minus sigma min divided by 2. So from this equation we find that sigma max minus sigma min is equal to 2 times sigma amplitude, so which is 225 equal to 450. So I have one is this equation, the other is this equation. So if I take these two equations and add these two equations, so get 2 times sigma max is equal to, because sigma min minus sigma min will cancel out, so it will be 100 plus 450, it will be 550. And sigma max then become 275 megapascal. So which will give the value of sigma min. Sigma min will be then from here, sigma max is 275 plus sigma min is equal to 100. So from here sigma min will be equal to 275 megapascal. Yeah, it looks like I have made some mistake over here. Sigma min will be equal to minus 175 megapascal. Okay, so these are the answers for the part A. Answer. So for part B, which is asking for the compute the stress ratio. So the stress ratio is R sigma min divided by sigma max. So stress ratio will be minus 175 divided by 275. So this will be equal to minus 0.636, and the compute the magnitude of the stress range. So the stress range is okay, we can find it here. Stress range sigma R is equal to sigma max minus sigma min. So it will be equal to 275 minus 175. So it will be 450 megapascal. A 12.5 mm diameter cylindrical rod fabricated from a 2014 T6 alloy is subjected to a repeated tension compression load cycling along its axis. Compute the maximum and minimum loads that will be applied to a yield fatigue life of 1 to the 10 to the power 7 cycles. Okay, so assume that the stress plotted on the vertical axis is the stress amplitude, and the data were taken for a mean stress of 50 megapascal. So this plot for the stress versus cycles to failure has been shown over here, although the values shown over here are for maximum stress, but let's take it for the stress amplitude. So 2014 T6 alloy is here, and its fatigue life is taken as 1 to the 10 to the power 7. So if you move along this line, and then if I plot a line parallel to here, so this is, you can take approximately equal to 160 megapascal. So the stress amplitude you can take as 160 megapascal. 160 megapascal. So which is basically sigma max minus sigma min divided by 2 is equal to 160 megapascal. So this means that sigma max minus sigma min will be equal to 320, and the mean stress is 50 megapascal. So sigma max plus sigma min divided by 2 is 50. So sigma max plus sigma min will be equal to 100. So solve these two equations. Just add these two equations, so it will be 2 sigma max equal to 420. So sigma max will be then 210 megapascal. Okay, so this sigma max is 210 megapascal. So now what we have to find is a 12.45 millimeter diameter cylindrical rod fabricated from this. So assume that the stress protein, and what we have to find is compute the maximum and minimum loads that will be applied. And then sigma max we have found, so sigma minimum will be sigma minimum plus sigma max plus 210 equal to 100. So sigma minimum will be 100 minus 210, it will be minus 110. Okay, so stresses we already now know. We now know the stresses. We know the diameter is 12.5 millimeter. So the load which will be applied, the load we need to find. Maximum loads which we need to find. So the force, so F max will be equal to sigma max 210 megapascal into 10 to the power 6 times 5 by 4 into 12.5 millimeters. So 12.5 into 10 to the minus 3 square millimeter. So in this case the maximum force will be equal to, that we can calculate from here. So the value of this force will be 25,771 Newton, or 25.8 kilometer. So, and then the minimum force, basically it will be the compressive force. It will be equal to minus 110 times 5 by 4 times 12.5 into 10 to the power minus 3 square meter square. So it will be minus 13,499